Hello, everybody. What I'm going to try to do in this video is go through some of the proofs of the facts that we learned in Chapter 7 and Chapter 8. I think if you take the time to watch this video slowly, it'll add a lot to your understanding about what you're doing. I would strongly suggest that you have a pencil and paper, and that you are slowing down and speeding up the video and pausing so that you can follow through carefully what I'm doing, okay? I'm going to be going through a bunch of different interfaces. I'm going to use Minitab. I'm going to be drawing some things on this PowerPoint slide, so bear with me as I sort of switch around. I don't really think you need to have Minitab up. I think the Minitab part of it, I think you can watch, and that'll be sufficient. So let me just give you an introduction. This is what I'm going to do in this video. So we're going to be talking about the least square regression line that we learned about in class. Remember, this is the line y hat equals a plus bx, which is the line that is minimizing the square residuals. And we're going to get back to that idea, but this is the line that makes the square residuals as lowest as possible. That's why we call it the least square regression line. And here are some things I'm going to prove. I'm going to prove to you that the line goes through what we call the grand mean, which is x bar, y bar. And that is a common sense idea. If you have a line and you put into it the average x, you would like to believe anyway that the line is going to predict the average y for you. So we would like this point to be on that line, but I will prove how we know for sure that's true. I will prove this formula. This is the key formula, that the slope is r, the correlation coefficient, times the standard deviation of y over the standard deviation of x. I will prove r is always between -1 and 1. It's impossible to get an r bigger than 1 or less than -1. It has to be a decimal. And finally, I will prove that r squared is the percentage of variation in the y data that's explained by the model in the x data. So these are the key sort of math facts in Chapter 7 and 8. And so hopefully this video will help you understand how we know that these things are true. So there is some prerequisite knowledge that I'm expecting you to have. First of all, real basic. From Algebra 1, I expect you to be able to square a binomial that a plus b squared equals a squared plus 2ab plus b squared. That's from Algebra 1. From Algebra 2, I expect you to know that for a parabola, y equals ax squared plus bx plus c, the x coordinate of the vertex will be at x equals -b over 2a. This is a fact from Algebra 2. If you've taken calculus, you can also know this by just taking the derivative of this and set it equal to 0. But if you haven't, in Algebra 2, you learned this fact. So just to demonstrate that for a minute, here is an equation. Y equals 2x squared plus 4x minus 1. And so I would expect by that formula that the the vertex would have an x coordinate of -b over 2a. I'll try to get a better color. Okay. In our case, it would be 4 is b and 2. So the b is the coefficient of the linear term, and a is the coefficient of the quadratic term. So in this case, then, x equals -4 over 2 times 2, which is -4 over 4, which is -1. So that is telling me that the vertex here is going to have an x coordinate at -1. And you'll see that, in fact, it does. Okay, so that's something you need to remember from Algebra 2. And, sorry. Okay, And then the last thing you need to remember is from chapter 7, you need to remember the formula for R. So R is 1 over n minus 1 times the sum of the product of the z-scores. And you'll remember we went through in chapter 7 why this formula made sense. We talked about quadrants in the standardized plane, and that if we multiply them together, the positive quadrants will give us positive numbers, and the negative quadrants will give us negative numbers. So review your ideas from chapter 7 to get this fact right here. Okay. So those are the prerequisites that I'm expecting you to know. All right. Now, you're going to see when I do this work that I'm going to do it in, like we did in chapter 7, I'm going to be doing it in the standardized plane. I'm going to be making z-scores out of the x and the y. And therefore, there are some facts about z-scores that you have to think your way through that we're going to need in this derivation. Okay, so the first one is this. The average of any list of z-scores is 0. So what I'm saying is if I take any list of numbers and I convert them to z-scores, their average is always going to be 0. Now think about why that's true. How do we get z-scores? We get a z-score. Remember, a z-score is just a number minus the mean divided by the standard deviation, right? Well, if the mean is something to begin with, and then we subtract that mean away from all the numbers, now the new mean is 0. That's all that's saying. Okay, so that is true. The average of any z-scores will always be 0. But if the average of something is 0, then the sum of those numbers has to be 0 as well, right? Because if the average divided by the number of numbers is, the average, is the sum divided by the number of numbers. So if the average is 0, then the sum of the z-scores has to be 0. Okay, next is the standard deviation. So if the standard deviation of some numbers is something, but then we divide all the numbers by that standard deviation, we're dilating it down. And so the new standard deviation is going to be 1. Can think about that for a moment. If the standard deviation of a list of numbers is something, and then we divide by that same something, we're going to have our standard deviation down to 1. If the standard deviation is 1, the variance, which is just the square of the standard deviation, also has to be 1. And then the last fact, this one is not obvious at all, but I'm claiming that if you take z-scores and square them, and add them all up, you will get the number minus 1. That's weird. So let me just think about that for a second. And it's going to come from this fact right here, that the variance is 1. So the variance, you'll remember, the variance is 1 over n minus 1 times the sum of a number minus its mean, that's it, squared. Okay, that's our formula for, I did that wrong, hold on a second. Okay, let me start again. The variance is 1 over n minus 1 times the sum of a number minus its mean squared. Okay, that's the variance. Now, if we're doing z-scores, it would just be this. And we know in a variance of z-scores equals 1. Furthermore, we know the average of any z-scores is 0, so this has to be 0 right here. So putting that together, I just get this. And now if I multiply by n minus 1, I get the fact I'm looking for, which is the sum of any z-scores has to equal n minus 1. Okay? So that's a little weird, but let's just verify these facts so that you're clear that they have to be true. Okay, so let me share with you. Whoops, that's not what I wanted. Yes, it is. So let me share with you. This is a Minitab screen. Okay. And I have this is just some age and weight of an animal. I think the age is in, I can't remember, it doesn't matter, but I think the age might be in months and the weight in pounds. This is just some species of animals. The context isn't that important here. Okay. And if I just look at some basic statistics here, you'll see the mean and the standard deviation are just some numbers. Okay, but what I want to do now is I'm going to standardize them. So I'm going to change them. I'm going to make a list of the age z-scores. Oops, misspelled that. And the weight z-scores. And I can do that pretty quickly. I'm going to go to calculator. I'm going to ask it to standardize the age and the weight, and I'm going to put them into the age z-scores and the weight z-scores. And I'm going to subtract the mean and divide by the standard deviation. And now they're all in z-scores. And now, if I ask it for the basic statistics of the z-score, we can see the facts that we showed on the other screen. So look at that. The mean is 0. That's what we said it was. And the standard deviation is 1 of any z-score list. Okay. So the variance has to be 1 too. I didn't list the variance here, but it's just the square of the standard deviation. Now, I did not show you that the sum has to be -1. So I'm going to do z age squared here. I'm going to show you that the square of any z-score adds up to -1. So let me just do that. I'm going to ask it to take to store it in that. And I'm going to ask it to take the age and square it. And what I claimed to you in the other screen is that these will add up to n-1. Since there are 10 numbers, I am claiming that this is going to add up to 9. Okay, so let's see if that works. I'll get stat, basic statistics, and I'm going to ask it to show me this. Sum wasn't on that list, so I'm going to hit statistics and just ask it for the sum. Make sure that's there, and I'm claiming the sum is going to come out to 9. Oh, look at that. Math works. Yay. All right, so that's just verifying these facts. All right, so we have the facts about z-scores, and we have those prerequisites, and now we're ready to start proving this, okay? And so let me just talk about what we're going to do. So first of all, here is the basic. I'm going to put a weight in the y variable and age in the x variable, okay? And here is the original graph. And you can see it's a fairly strong positive relationship. That makes sense. As animals get bigger, they get heavier. So, or older, they get heavier. So that makes sense. Okay. But I don't want to do the work with that. Okay. What I want to do is make the standardized plane. So what I want to do is I'm going to make a graph now. And it's going to be of the standardized plane. So in the y values, I'm going to put the weight z-scores. And in the x, I'm going to put the age z-scores. And I'm going to graph that. Okay. Now it looks about the same. The shape of the graph looks the same, but the numbers are different. Okay. So for instance, this point right here, 0, 0, that corresponds to the point x bar, y bar in this graph. Okay. And the units now are standard deviations. So this point right here, this animal is 1.13 standard deviations above the mean in age and 0.3 standard deviations above the mean in weight. So this is what we call the standardized plane. And what I'm going to try to do is show you how I know what the least square regression line that goes through this plane is. And then I'm going to undo the work that we did to make it into z-scores. Okay, so that's what we're going to do. And I'm going to walk you through the math now. Okay, so let me get on a whiteboard here. And let's talk about what we're doing. Okay, so we have a data set that's in the z-scores. So it's a data set that's in zx, zy. And I want to find the least square regression line. Okay, so that's going to be the line. And now I'm going to do everything in z. So z hat y equals a plus b zx. And what I want to try to do is I want to find a and b such that the square of the residuals is minimized. And the way I'm going to define that, you'll remember we talked about this, is the mean square residual, which is 1 over n minus 1. The residuals are the difference between the y and the predicted y. So in our case, it's going to be zy minus z hat y squared. And I want to find a and b such that that is minimized. And that's the math problem that I have. And now you'll see it involves a squared, which is why we had in the prerequisite being able to square things out. Okay, so let's try this. Okay, so now I'm going to take this mean square residual and I'm going to make a substitution because I know that z hat y equals a plus b zx. So I'm going to write this mean square residual and make that substitution. So I have 1 over n minus 1, the sum of zy minus a plus b zx. That's all of that is coming in for this zy. And I want to square that. And my question now is, what are a and b to make this as small as possible? And the first thing I'm going to do here is I'm going to distribute this minus sign and I'm going to rewrite the orders. So I'm going to write this like this. I don't want to mess this up, so I'm going slowly. Zy minus bzx minus a, all of that squared. So what I've done is I've distributed this minus sign and I've brought the zy and the minus bzx together and I've left out that a. And now I am going to square it using what we had as a prerequisite. So this is going to be the first term squared minus 2 times a zy minus bzx plus a squared. So that's just squaring out the binomial. And now my question is, how can I make this as small as possible? Okay, but in order to see this, you need to break this up. So here's the first term. And now I'm going to break this up into a bunch of terms. So I have this 1 minus n minus 1 is multiplied by the whole thing. So my first term is going to be 1 over n minus 1, 2a times the sum of zy. So that's 2a times the sum of zy. Then I have a minus times a minus, which is a plus. I still have the 1 over n minus 1. I have 2ab times the sum of zx plus 1 over n minus 1 times the sum of a squared. Now, think back to your facts about z-scores. What did we say the sum of any z-score is? The sum of any z-score is 0. So this term here is 0. It's not there. The sum of any z-score is 0. So this term here is 0, and it's not here. That makes this much simpler. So the mean square residual now is just this first term plus this last term. Now I want to focus on a for a second. I want to make a as small as possible. I want to make the mean square residual as small as possible. But what this formula is telling you is no matter what a is, for every point, you're going to be adding on a squared times 1 over n minus 1. So now you need to think a little bit about what value a has to be. Because if a is any number, be it positive or negative, you're going to be adding more stuff on in this last term, because any number, any positive or negative number that you square is going to be a positive number, which you're going to be adding more stuff onto this mean square residual. So the way we're going to make this as small as possible, can you figure that out, is if a is 0. If a is 0, then this term is going to be adding in as was going to be adding in nothing, and we're just going to have this part. So here's the first big fact, is that a is 0. What does that mean now? If a is 0, that means the y-intercept is 0, and that means that this line of best fit is going to go through the point 0, 0. Well, let me look at that for a second. So if that's right, what we just proved, in this line right here, it should go through this point 0, 0. So I think I can just ask it when I make the scatter plot. I'm going to ask it with the line. And again, I'm going to put the z-scores here. And if what we just proved is right, this is going to go through the line 0, 0. Let's try it out. Oh my gosh, it worked. So there's the first key fact. In the standardized plane, it goes through the line 0, 0. But what is the point 0, 0? Right? If it's going to go through the line 0, 0 in the standardized plane, what does that point correspond to in the regular plane? Well, 0 of a z-score is just the average. So what we have just proven is that it must go through, the line must go through the point x bar, y bar, because that's the origin in the standardized plane, which corresponds to the grand mean x bar, y bar in the regular plane, in the original data plane. And so that was the first thing you'll remember on the list of things I had to prove. That was the first thing I had to prove, which is that the line goes through x bar, y bar. And so that's how I know that's true. But of course, there are lots of lines that go through the point x bar, y bar, or through the point 0, 0 in the standardized plane. We have to figure out what the mean is. But we still have this part right here to minimize. So our next step is to figure out what b is, because now our mean square residual is down to this. So I am going to now clear that and say, now I have figured out the mean square residual is 1 over n minus 1, the sum of zy minus bzx squared. And again, I'm trying to figure out now what b is. We knew a was 0 in the standardized plane, and now we have to figure out what b is in the standardized plane. So again, I'm going to square this out. 1 over n minus 1 z squared minus 2b zx zy plus b squared z squared x. And now I'm just going to break this up. 1 over n minus 1 z squared y minus 2b 1 over n minus 1. I'm just breaking this up into 3 terms, plus b squared 1 over n minus 1 sum of z squared x. Okay, now let's think about our facts about z-scores. What's the sum of any z-scores squared? You'll remember we proved, and then showed on Minitab that always equals n minus 1. Likewise, this right here always equals n minus 1. Whoops, no squared there. No summation there. Okay, always equals n minus 1. Well, 1 over n minus 1 times n minus 1, of course, that's just 1. And then this last term, 1 over n minus 1 times n minus 1 is just 1. So that becomes b squared. And now let's look at this middle term. Well, what is this right here? That is r. So we have just shown now that the mean square residual equals this. Well, if you think about this for a second, this is a parabola. I'm just going to write it in a way that's easier to see. Here is a parabola, and I want to minimize that. So my question is, what does b have to be to minimize this? Well, you'll remember from Algebra 2, this was one of our prerequisites. This is minimized when b equals negative of negative 2r over 2 times this coefficient, which is 2 times 1, and we get this shocking answer, which is that b equals r. Whoa. So that's saying the correlation coefficient is the slope of this least square regression line in the standardized plane. So that means now that we have shown in zx, zy, the equation of the least square regression line will be y hat equals 0, because the intercept is 0, we proved, plus r times x. Or really simply, this is the equation of the least square regression line. I guess I should put z's here. This is the equation of the least square regression line in z. I don't like the way that looks. Let me do that again. So zy hat equals r times zx. So let's go back to Minitab now and see if that's actually true. So I would claim then that this line goes through 0, 0, and its slope is just r. So let's look and see. And if that's true, we can just like find out what r is here. Okay, so let's see. I'm going to ask it for this fitted line. The response is the z-scores. And let's see if that's right. Let's look at the line. This is saying r is 0.9246. Do they have r on this? They don't, but they have r squared. So let's just check that. If all this is right, 0.9246 squared should equal that r squared, which is 0.855. I'm just going to try that. You can try it on your calculator. 0.9246 squared. And if everything is right, that gives me 0.8549. I've checked it out. It seems to be right. So, wow. So we have just proven now that in the standardized plane, it goes through the point 0, 0. The line goes through the point 0, 0. And it has a slope of r. So that's pretty cool. And in fact, it wasn't really that complicated, right? It was just a little bit of algebra 1 and algebra 2. And now we know it's true. Okay. But we can't stop there because I don't want to do work in standardized scores. I want to do work in regular, in the actual data. Okay, so let's just think about this for a second then. We know this is true. We know that A is 0 and B is R in the standardized plane. And we've already talked about what this means in the regular plane. Since A is 0, it means the line goes through the point X bar, Y bar. That's one fact. But now let's think about this for a second. B equals R. Well, you just got to think for a little bit about what that means. Remember, slope is rise over run. So if I said to you, for instance, the slope of a line is 2, you would tell me, what does that mean? It means if X goes up by 1, then the Y goes up by 2, right? That's what slope means. 2 over 1, rise over run. Well, in this case, we have a slope of R over 1. But what unit are we in? In this, we're in standard deviations, correct? So another way to look at this is B equals R, standard deviations in Y, over standard deviations in X. That's what this is actually saying, isn't it? If B goes up one standard if we go up one standard deviation in X, our prediction is going to go up R standard deviations in Y, and there it is. That's the formula. B equals R SY over SX. Whoa. That was the second thing I had to prove. And in class, we, did some problems with this equation, but now you see why that equation is true. B equals R SY over SX. Okay, now I have a couple other things to do here. So next thing I want to talk about is I need to go back a minute. And I need to go back to this fact that we proved a little while ago, which is the mean square residual in the standardized plane is B squared minus 2R times B plus 1. And we have proven now that this is minimized when B equals R. Now, my next question is, what is the minimized residual? So I'm going to plug R in for B, and I'm going to figure out exactly what the minimum mean square residual is. So I'm going to make B equal R, so that's R squared minus 2R times R. I'm making B equal R plus 1. Simplifying, I get R squared minus 2R squared plus 1. r squared minus 2r squared is negative r squared plus 1, and I get this idea right here. So you have to think about what this means now. This means that when I draw the least square regression line, the smallest mean square residual will always be 1 minus r squared. And we did a little bit of this in class, but I want to review this for a little bit, okay? So the key idea here is that the variance in y is 1. You remember the variance of any z-score is 1. And I want you to remember that as we go through what I'm about to do, okay? So I want to come back to this idea here, okay? And I want to say, okay, let me, sorry. Technical difficulty, please hold. Here is a z-score. This is the standardized plane. If you think about the line at the mean, and since it's a z-score, the mean is going to be exactly at 0. And so this is the line, just y hat equals 0. And now, if you think about what the mean square residual is from that line, the mean square residual from that line is 1 over n minus 1 zy minus, I guess, z bar y, which is 0, right? This is the variance, isn't it? The mean square residual is the variance off this line right here, this mean line, and we have already shown that that equals 1. So if I just guess the mean for every point, regardless of what their x value is, I just guess their weight of the animal to be a z-score of 0, this is how much residual I'm going to have. This is how much error I'm going to have in that line. But we just proved if I did the same thing, let me change color. If I did the same thing, actually, but I did it to the line, now you can see clearly these blue line residual lines I'm drawing are smaller. But what we have just proven is that the mean square residual from the regression line is 1 minus r squared. So it's less than this amount. But it's less by r squared, exactly. So if we said that r squared was 0.92, that means if we just guess the mean to be 0, if we just guess for every point the mean value, we will have an error of 1. But if we guess it from the regression line, it's going to be 1 minus r squared, which I know r squared is 0.855. It's going to be 0.145, which is much less than this. In other words, guessing from the line did a much better job than just guessing from the mean. And in fact, how much better job did it do? Well, didn't it do r squared better job? It did 85% less. This number's 85% less than this number, which is why we say that r squared measures the percentage of variation in y that's explained by x. And before I go on, I should have said, by the way, I've just proven something else too. If the mean square residual is 1 minus r squared and it's squared, it has to be positive. So the only way this number can be positive is if r is between -1 and 1. That's how we know that fact that r has to be between -1 and 1. Forgot to mention that a minute ago. That just kind of flew out of there. But so what I'm showing here now is that R squared is the percentage of variation in Y that we can reduce this by. So let me show you that in real data now, not the standardized data, but the real data. So I'm going to now, because I'm going to go back to, wait 1 second. So I'm going to go, and now I'm going to make one of these fitted line plots, but I'm not going to do it with the standardized, because in the end, you don't want to have to standardize data all the time. So now let's just forget about the standardized, which we've used to derive all this. And now let's just go back to the original data. Okay, and what do we know about it? Well, the slope is not R anymore, remember, because the slope now is R times SY over SX. Okay, now you can verify that if you want, because we know R. We've already shown that R is 0.9246. And if you want to, you can do 0.9246 times the standard deviation of weight, which is 3.89, divided by the standard deviation of age, which is 1.974. And I get 1.823 should be the slope, which is what it is. Okay. Now remember, this is not 0 anymore, because now you have to put it through the line point x bar y bar. We did that in class to figure out what the new R squared would be. Excuse me, what the new y-intercept would be. But now I want you to focus on interpreting R squared in the context of the original problem. Okay. So I want you to look up here at these numbers that, that Minitab is producing here. Okay, it's doing this in sum square instead of mean square, but as long as you are comparing, it doesn't really matter which one you use. So let's look at this. Do you see it says total? Okay, this number here is the sum of this. Again, if I took the average of Y and drew a line at that line, and then said, okay, how far off am I every time? Squared it and added it up, it would add up to 136.324. But if I did the same thing for my red line, measured how far off I am on every single point, added them up. Let me get some space. That now is this, which is 19.782. So think about what that's saying. If I didn't know anything about the animal and I just guessed its weight, the average weight every time, I would be off by about 136. But if I knew the age, and now I figured out the predicted point value for each point, squared it and added them up, I'm only off by 19.78. I reduced the variation by 116.544. That's a lot because I started at 136.324. How much is that? Well, again, I'm going to get my calculator. 116.544 out of 136.324, that's 85.5%. That's what R squared is measuring. It's the percentage of variation in Y that can be explained by this regression. So this regression, knowing the age, explained 85.5% of this variation, which is a lot because it's a strong relationship. But it's not everything. There are other things because there's still error in the line. How much error in the line? That's this 19.78. That's about 15%. So 15% is explained by other things besides the age. So I think that's pretty much all I had to do. That's a lot of stuff I just did. So let me go back here. And let's just go back to what I said I was going to prove. I was going to prove that the line, this least square regression line, passes through x bar, y bar. And I did that by first showing it pass through 0 in the standardized plane, 0, 0, which corresponds to the point x bar, y bar. Then I said I would prove that B equals R times SY over SX. We did this by showing in the standardized plane B equals R. Then I said I would also show you why R had to be between -1 and 1. This had to do with the idea that the mean square residual in the standardized plane was 1 minus R squared. Since it's squared, that has to be positive, which means R has to be a number between -1 and 1. And finally, I would show you how I know that R squared is the percentage of variation in the Y data that can be explained by the model based on the X data. So those are the things I said I'd prove. And hopefully, if you watched this carefully and wrote stuff down as you're doing, you have more insight into how I know these things are true. And with that, I will say goodbye.